Let's think about springs. All right, let's think about springs, which are coiled pieces of metal strips. But really, springs are everywhere. They're guitar strings and harp strings and piano strings. They're things like pendulum. A pendulum is it's in a clock. It's a mass on a stick basically, and that's going to oscillate as well. It's going to wiggle back and forth. So that's one word, vocabulary word oscillate. That's going to be for that sort of persistent rocking back and forth. That's an oscillation. All right, so what are we looking at on this page is let's just start over with our force formula. Our force for a stretched or compressed spring that obeys Hooke's law, and that's another way to say that is it's linear. And another way to say that is you can write this equation. So F for force, and that's a minus kx. K is the spring constant. And what's it going to be? Its units, probably. That's a distance, so it's going to have to be coming out in a force unit. But you're multiplying by a distance, so it's going to be newtons per meter. For that spring constant, it's going to depend on what kind of spring you've got. That's basically it. So you've got to calibrate your spring. X, that's displacement, that's distance, but it's a special one. It's going to be along the stretchy axis of the spring. And it doesn't really matter which direction you think positive X is in. It's going to work out either way. Okay, to the cartoon, this could be looking down on a spring, or you could hang these springs. It's okay, however you think of it. Let's suppose we had a relaxed spring here. And so that's where you need to put your 0. So when that situation is in equilibrium, that's x equal 0. So that position that's our relaxed spring right there. And if we've got positive x going that way, then if you pull on that, you're gonna stretch your spring downward. So you can imagine at this point you've got a force vector, but that force is wanting to restore the spring to its relaxed position. And then if you press on the spring, you compress it like that, then that spring also wants to relax to its position here. So that in that case, the force is like that. So hence, if that's a positive x, that's the positive x directions, but this force vector is the other way. So that's why there's a negative sign in there. Just to keep the directions straight because it's a vector. Okay, we actually had this before when we chapters and chapters ago in the dawn of history. We actually had this before. We also had one more thing about springs, and that was a formula for the potential energy of a spring. And we took this force law, and we said, well, it's going to be basically force times distance is work. And then we figured out that, well, it's no fair because we had no force at the beginning, and then we had full-on kx force at the end. So let's take the average of that. So there was a there was a 1/2 in there. So 1/2 k x squared. That was our formula for the potential energy of stretchiness in a spring. If you stretch your string by x amount, then this is the amount of energy stored in there. And that's so if we stretch this thing out and then boing, let it go, then when it hits x equals 0, it's going to transform that potential energy into kinetic energy. And so we did that a little bit back in the day. We took that formula and then set that equal to kinetic energy 1/2 mv squared to find velocities and so forth.